Well, your your paper has been published in Science Advances.
Mhm.
That's a pretty big deal.
Yep.
It's a real,
Yeah.
yeah. For anyone who doesn't know, science is
Mhm.
what science and nature. Am I right in saying are the two biggest, most influential scientific journals in the world?
Yes, and they cover all of science basically. So if you've got kind of an interesting enough finding, regardless of kind of field within science, within the field of science, you can have a chance. So, but yeah, so we kind of chose to kind of go high, so to speak, because it is quite attention grabbing. It's quite a big thing for how we see kind of all of life in general, possibly. So that's kind of why we picked the kind of a bit kind of more high profile than otherwise. But yeah.
Why is it? Why is it
Mhm.
so? Why is it causing? Why is it a big deal? Why is it high profile?
Mhm. So we haven't really. There isn't an example of like an organism that went extinct that we doesn't have as close a relative alive today as Prototaxites. Arguably, I think that is a kind of new thing. As I mentioned, there are the kind of frond-like Ediacaran organisms that are a bit similar, like this, but I think because of how much we can know about Prototaxites, we can know about its chemistry and its anatomy down to very, very small details. I think that is a thing that really makes it special because it's doesn't have any parallels today in terms of how it built its kind of complex bodies. Um, but we can know so much about it. So I think that's the really special thing.
Why? Why can we know so much?
So it's how the fossils are preserved. So this is the fossils that we focused on in our study they're from Aberdeenshire. They're from near the village of Rhynie. So it's a kind of place called the Rhynie Church. So it preserves this whole range of organisms. So plants are the main thing that it's kind of known for, but a whole range of organisms, really amazingly. So down to the cellular level, you can even see cell division happening, and they're like 410 million years old. This kind of fossil deposit, and it's so it was kind of what I did my PhD on. Basically, I came in looking at the plants, and then we kind of got this new specimen, and then it kind of got a bit off track. But so because you can know so much about the anatomy and also chemistry as well, because of how well preserved it is. So it's preserved through the activity of like a hot spring. So kind of Yellowstone is kind of the analogy that people kind of know about, where all this kind of mineral-rich water comes out and then it solidifies, and it solidified around the plants 410 million years ago, and everything else as well, the Prototaxites, and really locked in the structures and the cell walls as well. So that's how we can know so much about it. So it's a kind of a convergence of like having a very good, an interesting kind of organism to look at, finding a Prototaxites, and also finding it so well preserved that really kind of was the thing that allowed us to even try to do this study. Try to do this study. So
the hot springs. Yeah, I was reading about the Rhynie
yeah.
shirt last night, and again, also seems very, very, very significant. So there were hot springs that were producing minerals.
Yeah,
and that made a kind of layer that then preserved all the life that was there.
Yeah, so the water kind of got through into like for the plants. It's probably the easiest thing to kind of explain, where it kind of would have got through into the tissue, and so it's kind of like how things are sometimes petrified as well, like with like wells where they have the mineral rich wells, and you can find like you hang something up and then it comes out and it's like really solid because it's had so much kind of mineral deposition in it. So that's kind of basically the same thing, aside from quite different, but that's kind of the same principle. So that's how they became so well preserved, basically. And it's a very special type of preservation, which is not really that found. There's not really that many close equivalents found elsewhere in the world. So it is quite a special thing that Scotland has, really, this like amazingly preserved and really important kind of fossil deposit. So yeah. we're a big fan at them. It's been a lot of my supervisor's work has been on it. So my PhD supervisor.
Is that Dr. Hesman?
Yes. So a lot of his work has been on the plants of the Rhynie chert and finding out what we can know about them for the evolution of plants in general, because they're so well preserved that you can very closely compare them to living plants as well. Because in the best cases, obviously there's kind of bad preservation sometimes, but in the best examples, which are quite numerous really, you can see all the cells, so you can compare them to living plants that you kind of prepare the same way. So if you kind of cut it up, it looks very similar to the Rhynie chert plants, except they don't, because the Rhynie chert plants are so strange, and that's kind of how it adds to the kind of evolutionary story of plants. Whereas Prototaxites, we don't have anything that actually really closely parallels it to compare to. But that was, again, the point of our study, because it's so well preserved, we can look at it comparatively to what fungi look like today, and we can kind of show that it looks very distinctly different. So, and also the chemistry of the cell walls is still locked in there as well. So we can, even though it has changed over time, I mean, it's 410 million years old, and it would have been exposed to relatively warm water, because it's a hot spring. Not we don't think it was really like the kind of giant Yellowstone kind of scenario necessarily. It wasn't really intense probably, but it would have been changed a little bit. So we have to compare the chemistry to everything else that we see in the Rhynie chert, the chemistry of the Prototaxites to the chemistry of the fungi in the Rhynie chert that has been exposed to the same thing that's also 410 million years old. And so the ability to compare this whole kind of community of organisms is also what our study had as a key strength really, which was this is work done by Corentin Laurent, who is the first listed author in the paper, and his kind of specialism is looking at the chemical signals of fossils. So that was his kind of a real focus on this paper, and because all of these organisms, the plants, the fungi, there's bacteria, there's little arthropods, so kind of insect-like organisms, and other things as well that we could compare to chemically. And Prototaxites really stuck out as being completely different from everything else chemically. So that's really what it's kind of perfect kind of experimental conditions really that we got from this fossil deposit. So.
And was this like a new thing? Was it recently discovered? How did it come up? Why is it now that this has been published and everyone's hype about it?
Do you mean like the specimen or the techniques?
The specimen.
So the
fossil.
The specimen was a kind of newly found one. So the Rhynie chert is now a field basically. It has been. It was kind of initially identified when in the 1910s, someone called William Mackey just found some little rocks kind of just on the ground around the village, and saw they had plants in them, and then kind of they dug into the kind of fossil site and pulled out a load of rock. So we're still kind of working on all of that still. But this new specimen was found kind of around the actual site. So the actual Rhynie chert site is it's a triple SI, so you can't really, only with permission you can actually kind of dig there, but around kind of around Rhynie generally, you can kind of find in the soil as well, just kind of these loose blocks of Rhynie chert. And so this is an example of one of those that was found and was given to my supervisor through this kind of arrangement of donating kind of important specimens that people find through to people who can research them. So this was a kind of a new specimen, and it was larger than any Prototaxites known from the Rhynie chert before, there was a couple of kind of very fragmentary, I say this, maybe this big, very fragmentary specimens in you can only look at it on slides, whereas this one was still pretty small, but probably about, the size of a mug, I think is probably the good comparison of what we had in this rock, which compared to everything else, which was lots of small plants and lots of small kind of bugs and arthropods, is quite big. So it's also the size of this specimen that really allowed us to do a lot of things with it. So we could take samples for looking at the anatomy, take samples for looking at the chemistry, and still have, you know, enough left. So that's because it was a new specimen and it was so big is also what helped this study come about. So
So do you have to like take it apart to see what's in there?
yes. So one of the things about, I mean, it's kind of the advantage and also the disadvantage of the Rhynie chert is how well things were preserved means that they were locked in very well and it's hard to get them out. So the kind of normal way that people have been studying it since the 1920s is by cutting up into thin sections. So you have to use a diamond saw, which is quite intense. You have to cut through the rock. It's silica, so it's very hard. And then if you want to look at it through the microscope, you have to then make it very thin, so under a centimeter thinned, so the light can pass through. So that's kind of the typical way that people look at it. But that is destructive because you are cutting it up and you're losing a fair amount just by kind of polishing the section. And then there's even more kind of destructive ways to test the chemistry, where you dissolve the specimen in acid to get the organic matter out, so that you lose the silica, but you keep the cell walls and what's left of the cell walls. So yeah, it's kind of you do have to sacrifice some of your samples, so you have to make kind of carefully considered decisions about what you keep and what you use. So yeah.
That is, yeah. I can imagine with a 410 million year old piece of important scientific fossil. That must be quite stressful.
Especially as it was this one was one of a kind, since especially when since it's hard to know what's in a lot of the Rhynie chert before you cut it up anyway. Whereas this one we could see very clearly there was some large thing on it, like the largest thing that it really exists in this kind of these sort of fossils. So then we had to be careful and document the whole thing. I made like these kind of 3D models of the rock at all sorts of different stages, so we do have that record of the rock before it got cut up. So